Okay, there we go. So as we can see, I am always forgetful to start recording. So if somebody just wants to always remind me in the beginning, that'd be wonderful. I'd love that because that way we don't miss information. So thank you. Okay, so just to restate the question was for question 15, wouldn't all of the domains be the same? And in fact, a lot of the domains are going to be similar, but there's going to be two. So if you think about them in parts, there was 5 questions for 15, right? There was the addition, the subtraction, the multiplication, and then 2 different divisions, right? So there's 5 parts in total. 3 of those parts are going to have identical domains. So let's just go through 1 or 2 of them together, so that way we can see the identical domains, and then we'll do the other ones that don't have identical domains. Okay, so for example, the first one is the addition of them. So we see, and I'm not sharing my screen. That would be really helpful if I did, right? Okay, we should be sharing now. There we go. Okay, so we're starting with f of x is equal to 2x minus 1, and g of x is equal to the square root of x, right? Okay, so with this, the first thing that we have to do is the addition. So we do the addition, we say f plus g of x. What this really tells us is we take both of our functions, f and g, right? This tells you you have your f function and you're adding to it your g function. So this just says, okay, well, your f function is this, right? Your 2x minus 1. So you're just going to write 2x minus 1 over here. And g, you have your square root of x. So we add the square root of x. And when you get to this point, you should ask yourself, is there anything else that I can simplify? Is there anything else that I can do? And the answer is no, right? The answer is you can't add anything. If, hypothetically, please understand this is only hypothetical, so I'm going to write this in red. If hypothetically g of x was just an x, not a square root of x, then yeah, you could do some condensing. And why can you do that? Well, that's because the x's would have matching exponents of 1, right? But we know from previous chapters that square root, what this means is you have an exponent of 1/2. And you can't combine, even if it's the same base, you can't combine numbers together if they have different exponents. You would have to change the exponents first, so that way you could combine them. So as a result, you would just leave it as either square root of x or x to the 1/2, however you wanted to leave it. I imagine many of you would have left it as square root of x, and then that's just it, right? So for the purpose of this, we'll just leave it as square root of x. And now, conversely, or similarly, I should say, the subtraction, f minus g, is going to be incredibly similar, but the only difference is instead of a plus sign, you're going to have a minus sign, which means that instead of a plus sign here, you're going to have a minus sign here. Okay? But we're talking about the addition, so we'll just leave it as addition. And now to figure out the domain of this, you just have to ask yourself the same 2 questions that you're always asking yourself when it comes to domain. Number 1, if I have a fraction, then can the denominator be 0? And we look at our equation or our function here, and yeah, there's no fractions, right? So you don't have to worry about that. But we do see that we have a square root, and our second thing when it comes to domain, the second item, is can we get a negative number underneath an even powered root? Once again, this is a square root, which means that this is in fact an even powered root. So yeah, you do have to worry whether or not you can get a negative number. So what you want to do is you recognize that this is your problem. So you just do the same thing that we always do. You set whatever is underneath your square root to be greater than or equal to 0, because in that way, you know that you'll solve for either getting 0 or a positive number. You're basically excluding all the negative numbers. So we set everything that's underneath the square root to be greater than or equal to 0, which in this case, oh yeah, this is really easy, right? It's already done for you. There's no work that you have to do. It's just x. So x is greater than or equal to 0. And in interval form, what this means is 0 to infinity, right? We're talking about starting from 0 and all the numbers that are bigger from 0, and just referring back to the midterm, when you guys were writing interval notation, I noticed another mistake here. Some of you were writing your values from like greatest to least. So like I saw like from 5 to -1, for example. You always have to write from least to greatest, always. You read a number line from left to right, that's how you have to write your interval. Okay, so we write it from starting from 0 to positive infinity. Okay, and now what does this tell you? Well, this tells you that the domain, if you were to graph it, which you didn't have to, but if you were to graph it, your domain, starting from 0, is all the numbers, including 0, that go on forever, right? No negative numbers at all. If you had a negative number, sure, plugging in a negative number would work here for your 2x minus 1, but then you would also have to plug that same negative number into the square root of x, and that's where you'd have an issue, right? If you tried -1, for example, you would have 2 times -1, and that's acceptable, but you would also have square root of -1, which is unacceptable, which we know you can't have a square root of a negative number.
Can I like build on my question?
Sure.
Okay, so in the lecture, didn't you say that in order to find the like domains, I know you said for like composite functions and combined functions, it's different, but since this is a combined function, didn't you have to do like set f of x equal to 0 and then find that 1/2 couldn't be, like couldn't be a solution? So wouldn't you have to like exclude 1/2?
So let me ask you this then. Why do you think 1/2 couldn't be a solution for this?
Because x, when you equal 2x minus 1 to 0, 1/2 is your solution.
Sure, but is 2x minus 1 in a denominator of a fraction?
Oh, no. Okay, thank you.
Yep. So remember, that's a great point. You do always want to try to find a point where it could be 0, but that only applies if that happens in the denominator of a fraction, because you can't divide by 0. So that's your first constraint when it comes to domain. But because we don't have fractions, you don't need to worry about that here. So your domain is just going to be from 0 to infinity, including 0. And now you're going to recognize that because the only thing that's changing for the subtraction one is that you're making the plus a square root of x to be a minus square root of x, well, your problem is still with square root of x, which means that for the subtraction one, your domain is going to be the exact same thing. And then when you multiply them together, similarly, the same problem is going to be the same problem. Your problem when you multiply them together isn't going to be with the 2x minus 1. It's going to be with the square root of x. So you're essentially just finding the domain of square root of x 3 times, which in all 3 cases is from 0 to infinity. So the first 3 operations that you're doing for question 15 all have the same domain. Okay, now let's do one where that's not the case. Let's do the next one, which is D, which I know I didn't label for you guys, but that's f divided by g. So what is f divided by g? F divided by g is, well, you take your first function, so this is f of x, and you divide it by g of x, right? So that's where we have 2x minus 1 divided by the square root of x. So now you see we actually do have a fraction. We have a square root and also a fraction. So what does this tell you? This tells you that you're going to be checking off both of those domain problems, right? You're going to have both the problem of the same problem that we had with the first 3 operations. You can't have a negative sign underneath of the square root. And also you have to check and see when you get 0 in the denominator. Because if you get 0 in the denominator, you're dividing by 0. And when you try plugging that into a calculator, for example, you're going to get an error, right? You can't divide by 0. So what we do is we ask ourselves, is there a problem in the numerator? And you say, okay, numerator, there's no square root, and I don't care if I get a 0 in the numerator. If I get a 0 in the numerator, that just means the fraction is 0. So yeah, sure, that doesn't matter. My numerator doesn't matter to me at all here. However, my denominator definitely matters because, again, I could get a 0, and also that's where I have the square root problem, right? So what we want to do is we want to find all the numbers that make the square root okay. So what types of numbers are that going to be? Well, that's going to be positive numbers and 0. However, we can't have 0 because of the first constraint for domain, which was we can't divide by 0. So essentially what we're saying is we're just going to set x to be greater than 0, strictly greater than, because again, we have to make sure we get rid of the negative numbers and also get rid of 0. So you set whatever is underneath your square root to be greater than 0, but again, super easy, right? What's underneath the square root is already just x. It's already isolated, which means your domain is going to be from 0 to infinity, but notice the difference. It's a parentheses for 0 this time, which means we're not including 0. 0 is not allowed in our domain for this equation or for this function. So are you starting to see the difference? I think it was Gabriella who had asked originally.
Yeah, I understand now. Thank you.
Great. Okay. So that should do it. And then the last one, which is G over F, that one is where your idea of having to solve for the 2x minus 1 is going to be part of your domain, because notice how 2x minus 1 is now in your denominator. So 2x minus 1, you have to find where that's 0. And then also you have to get rid of the negative numbers because of the top part, right? The square root of x is, still a problem. Okay, so I don't want to spend too much time going over that. I think we had another question in the chat, right? Yes, Keji asked for number 50. Okay, sure. Give me 1 second. Just want to make sure I actually see what number 50 is. Be good for me to see. Okay, 50. So there were a couple parts to 50. So let's see here. Let me clear this off. Okay, so first off, we're given f of x is equal to x minus 1, and g of x is equal to x over x plus 1. Okay, so what do we have to find? We have to find two different things. So we have to find f composed with itself, so f of f, and we also have to find g composed with itself, so again, g of g. And then what we have to do is we have to find the domain of each composite function, okay? So how do we do this? Well, the first step is obviously find what the compositions are. If you can find what the compositions are, that'll make finding the domain easier, because you have to do that step anyway. To find the domain of a composite function, as we learned, the first step is you find the domain of the inside function, and then you find the domain of the composite function after you've plugged the inside function in. So what we're going to do is we're going to solve for f of f, and we're going to solve for g of g first, and then we'll figure out the domains from there. Okay, so let's do f of f first. So f of f, this one is a little bit easier. So reading this from left to right, well, even though it's f composed with itself, you still read this the same way, right? Your furthest left function is going to be your outside function, so you have f, and now you're going to have your middle function, or the the one next to it, so to the right of it, that's going to be your inside function. So f of x. Okay, so you do the same thing that you would normally do if these were two different functions. First, you take your first function, your inside function, and that's going to be your input, right? So we see what is f of x. F of x is x minus 1. So that means we're going to be plugging in here f of x minus 1. Everybody see the substitution that I made? All I did was I looked and I saw what f of x is equal to, and now that becomes my new input for the outside function. And now all I have to do is I now have this new input, which again is x minus 1, and I have to go back to my function f, which is the same thing, x minus 1, but I'm plugging in this entire piece, x minus 1, wherever there is an x. So that means I'm plugging in x minus 1 into that x. So we know that this is going to give us x minus 1 minus 1, right? We still have this other minus 1 that dropped down from plugging into our function the second time. So we have x minus 1 minus 1, which just simplifies to be x minus 2. Any questions on this before we move forward? All this is really just plugging in values, recognizing that you get a new input, and plugging in that new input into a function. If you have questions, you should stop me now, because it's only going to get more complicated. Okay, taking silence as we're good, which may be a fault of mine, but that's how we have to proceed. So we have x minus 2 now. Okay, so we have now solved for f of f. Let's now solve for g of g before we move forward. So g of x, once again, you read it from left to right, which means you have an outside function of g and an inside function also of g, because it's g composed with itself. So we look and see, what is g of x? Well, g of x is x over x plus 1, which means that we are going to be plugging in to our outside function x over x plus 1. Okay, so our goal here is we have this fraction. We have this x over x plus 1. This entire fraction is going to serve as your new input wherever there's an x in your g function. So we look and see how many x's are there in g originally. There's an x here, and there's an x here, and then there's going to be that plus 1 that just drops down, right, in the denominator. So that means when you make this, you're going to get a complex fraction. In the numerator, because there was just an x by itself, you're plugging in your input for that x. So that means you're going to get x over x plus 1. This used to be an x. Now we plugged in our input of the fraction. And we have that same input, again, because we had an x in the denominator, but we have that plus 1 that carries down. Again, if you're comparing this, think about this, each circled piece, as it just being an x originally. So notice how this is corresponding to your function g of x. You're just taking your input, which in this case is a fraction, and plugging it in wherever you have an x. So you have x over x plus 1. Okay? Okay, so moving on from there, what we have to do is we have to simplify this, right? This is a complex fraction. We can't have complex fractions. So simplifying this, you can do it in a couple ways, but we can, obviously try to go through it just the fastest way here. So one of the fastest ways that you can do it is you can recognize that you already have a common denominator of x plus 1. So if you multiply the top and bottom by x plus 1, you simplify this greatly. If you don't see that immediately, then just take it one step at a time. What's your first step? Well, your first step is simplifying the denominator, right? And how do you simplify the denominator? You have a fraction plus an integer. And what do you know about that? Well, you know that you're going to need a common denominator for this plus 1 over here, so that way you can combine it with your other fraction. So if you want to take it one step at a time, that's totally okay. And I'm just going to replace this 1 with an x plus 1 over x plus 1. Why can I do that? Well, again, I'm just making common denominators. I know I need an x plus 1 in the denominator, so I multiply 1 top and bottom by x plus 1. And we know that if we wanted to go backwards, x plus 1 over x plus 1, it's the same number on top and bottom. So we know that that would simplify down to be 1, which is what we started with. So great, we now have a common denominator, which means we can simplify that denominator. So we have x over x plus 1 on the top. And now we have, well, now that you have common denominators, you can just add the numerators, right? So we're adding this x, and we're adding it to x plus 1, and we keep the denominator piece the same. So we know we're going to have x plus 1 on the denominator, and we know we're going to have x plus 1. So how many x's are we adding? X plus x, which gives us 2x, and then we have that plus 1 just hanging around. Okay, well, now you're at a point to where you can use keep, change, flip, right? You have a fraction divided by a fraction. Keep, change, flip. If you wanted to, you could also simplify, because you could recognize you're dividing by x plus 1 twice. So you could, again, multiply top and bottom by x plus 1. But if you don't see that immediately, that's okay. So keep, change, flip. What that means is you're going to have x over x plus 1. You're keeping that fraction the same. You change the division to a multiplication, and you flip the other fraction. So now it's x plus 1 over 2x plus 1. Okay, almost done here. So now you recognize, oh yeah, you have the same factor here on top and bottom, which means, yeah, you can just cancel those out. And canceling those out, you're left with x over 2x plus 1, and there's really nothing else that you can do here. This is it in simplest form, right? There's nothing else you can do. It's done. Okay, so as a result, you now have x over x plus 1, and I'm sorry, x over 2x plus 1. So you've solved for g of x. You've solved for g composed with itself. Again, the entire key to this was just recognizing how to plug in your input into your x's, and then you recognize that you get a complex fraction. You handle complex fractions the way that we handle all fractions, which is you get common denominators. And then once you have it in the form of one fraction divided by a second fraction, you can keep, change, flip. Okay, any questions on this so far? I'm running out of time before the quiz is supposed to start, so I just want to hit domain on this real quick. Yes, Deborah?
If it was a 2 instead of plus 1, would you be doing the same thing?
I'm sorry, can you repeat that?
If it was a plus 2 instead of a plus 1.
I just want to follow where you're saying a plus 2.
At the denominator.
So you're talking about, right, like here, for example?
At the top.
Okay, so
The step before that.
the step right before it. Okay, so you're talking about like right here when you're plugging in your input. X.
Yeah,
plus.
but the denominator.
Okay. denominator. I'm following you now. Okay, so if you had x over x plus 2 instead.
No, x over x plus 1 plus 2.
Oh, plus 2. Oh, I'm sorry. Okay, so instead of it being a plus 1 over here, if you had a plus 2, you're saying, hypothetically?
Yeah.
Okay,
Yeah.
so, yeah, so what you realize is that 2 is the same thing as 2 over 1, right? You can make any integer into a fraction, and then what you do is you just get a common denominator again. So what's your denominator that's in common between x plus 1 and 1? Well, that's just x plus 1. So you multiply top and bottom by x plus 1.
Oh, okay. Thank you.
Yep. So the only difference is that you're now going to have an added factor of a 2 being multiplied in the numerator, but easy enough to handle. It's not that bad. Okay, but good question. Okay, so I'm just going to rewrite this x plus 1 over x plus 1 because we knew that was the plus 1 that we had. Okay, so domain. Right before our quiz starts, I really want to make sure that I hit on this. So to find the domain of this, first, and I'm going to skip domain of f of f because this one is kind of fairly easy. I think you guys can figure this one out on your own. So the way that you handle domain of a composite function is you do the domain of the inside piece first. So domain of g of x. So that's our first step. Domain of g of x, which I'm going to abbreviate as just domain with just a d, right? So domain of g of x, well, we look at g of x and we ask ourselves, where is the problem? What could happen here? There's no even roots, so that's out, but it is a fraction, so you have to care about the denominator. So we set our denominator equal to 0. So x plus 1 is equal to 0. Solve for x. X is equal to -1. So this tells you that all points are going to be okay except for -1, which you write as -infinity to -1 union with -1 to infinity, right? We're talking about all the points to the left of -1, all the points to the right of -1. We're just excluding -1, which is why there's parentheses there. Okay, so now that you've figured out the domain of the original, and now that we already plugged in g of x, right, we solved for it, now we just need to find the domain of the composite piece. So finding the domain, well, it's going to be the same restriction, right? We're not caring, there's no square root, there's no even root, so you don't have to worry about that, but we care about when the denominator can be 0. So you set your denominator to be 0 once again, 2x plus 1, which means you're solving for x again. So you have 2x is equal to -1, and divide by 2, you get x is equal to 1/2. Okay, so what does this tell you? This tells you, and again, if we're writing this in interval notation just for this piece, it's from -infinity to -1/2 union with -1/2 to infinity. All the points that go to -1/2 and all the points that go to from -1/2 to the right to positive infinity. So when you compare these two together, these two domains, you recognize, okay, what I'm really saying is I can have all the possible numbers in the real numbers except for these two numbers. The only numbers I can't have are -1 and -1/2, right? So when you're making your final domain is going to be all of the possible numbers, right? Starting from the left, so -infinity, and then you hit -1, right? And we know from the first domain that you can't have -1, so you stop there and you say, okay, parentheses. We have to stop at -1, it's not included. So we put a parentheses, we start our next interval, which starts again from -1 because we're not including it, parentheses again, and then we go up until we hit -1/2. We do the same thing, right? We hit a number that we can't have in our domain, so we exclude it from our final domain. And now we go from -1/2 to infinity, and this is going to be your final solution, which I can't circle the whole thing. There we go. Okay. So hopefully that makes sense for you guys. The entire idea is you're taking into account the two different domains, and you're just basically getting rid of those 2 points in particular. All the other numbers work for both the original and the composition. Okay, so I'm going to go ahead and stop recording and stop sharing my screen here. The quiz is up, so you guys can go ahead and check Blackboard. Again, it's under exams. Go ahead and get started on that. You have until, basically the end of class to complete it. And I will stick around as always, and I will always email you back letting you know that I have received your quiz. Okay, so good luck, guys. And once you're done, feel free to exit the class. I will talk to you on Monday.